This is Applied Calculus, Section 3.6, Related Rates, and problems that find the rates of change of two or more related variables that are changing with respect to time are related rates problems. And related rates problems often implies that our derivative is going to be respect to the t variable, so we'll be taking the derivative with respect to d dt. And it is good to be familiar with a variety of geometric formulas because it is these geometric formulas that will often connect our variables in our related rates problems. So the table below lists examples of mathematical models that involve rates of change. For instance, the rate of change in the first example is the velocity of a car. And we can see that x is the distance traveled, but dx dt is the velocity. So when you're going 50 miles per hour, that is the change in position as time is changing. The second one is describing water being pumped into a swimming pool at a rate of 10 cubic meters per hour. So we're discussing volume as time passes. So V is the volume, but dV dt is the volume per hour. And the third one discusses a gear that is revolving at a rate of 25 revolutions per minute. And theta is the angle of revolution, and d theta dt is the revolutions per minute. So we're talking about the value of our variable and the value of how our variable is changing. So this first example is a classic one for related rates problems. It states that a 26-foot ladder is placed against a wall, as shown in figure 1, if the top of the ladder is sliding down the wall at 2 feet per second. Notice that is a rate that is describing how the top of the ladder is changing with respect to time. It then goes on to say at what rate is the bottom of the ladder moving away from the wall. So we have the ladder moving down the wall and the ladder moving away from the wall. And it says to calculate this for when the bottom of the ladder is 10 feet away. So this is a position value, not a rate of change. This is a rate of change because it's relating it to time. So it's always helpful to give a drawing and a coordinate plane. This is my y-axis, this is my x-axis, and the ladder is 26 feet. That is not changing, so there's no rate of change there. The ladder is always 26 feet. So we can say the ladder equals 26 feet, and the ladder sliding down is dy dt, and the ladder sliding away is dx dt, and at each position there is an x and y location. So we see that this forms a right triangle, and the Pythagorean theorem is going to link this problem. So we can say that x squared plus y squared equals the hypotenuse, but the hypotenuse is a constant, so 26 squared. And if we take the derivative of everything with respect to d dt, now we see our implicit derivatives popping into our related rates problems. We see that the derivative of x squared becomes 2x dx dt. The derivative of y squared is 2y dy dt. And the derivative of a constant is 0. Well, we go back, we keep reading the problem. We see that they gave us a value for dy dt. So I'm going to plug in 2 feet per second, but it said it was sliding down, so that's a negative 2 feet per second. They gave us a value for x, and because it's the Pythagorean theorem, when x is 10, if we plug it in, we should be able to solve for a y that goes with it. So 10 squared plus y squared equals 26 squared, and you should find that y is 24. So we're going to plug 24 into y. And if you look at this related rates problem, we know everything except dx dt, and that is what the problem is asking for. says, at what rate is the bottom of the ladder moving away from the wall? Well, that's what the dx dt is describing. So we want to isolate the dx dt. And we see that 2 times 24 times negative 2 is negative 96. But when we move it to the other side, that's a positive 96. And our x value was 10. So 2 times 10 is 20. And that gives us 4.8 feet per second. So because that's positive, we see that the positive values for the x-axis are to the right, and that is away from the wall. So it's moving away from the wall at 4.8 feet per second. This next slide is just the textbook's list of suggestions that you should implement while solving related rates problems. Step 1, sketch a figure that is helpful. I used a coordinate plane with the ladder. Step 2, identify all of the relevant variables. We used x and y for the height on the wall of the ladder for y, and the distance from the wall on the ground for the variable x. We also included rates that were given, dx dt and dy dt, but we had to make sense of them. Moving down the wall is negative. Moving up the wall would be positive for dy dt. And moving away from the wall was positive for dx dt, but moving towards the wall would be negative for dx dt. Third, it says express all the given rates and rates to be found as derivatives. We did that using d dt. Step 4, find an equation that connects the variables. We used the Pythagorean Theorem in our example. 5, we're going to use implicit differentiation with the equation and use either chain rule or product rule or whatever rules are appropriate. And 6, solve the derivative that will give you the unknown rate and also substitute whatever values back into it as we did. So this is just the book's list of suggestions. Let's do a couple of more problems together. So here's a second problem. It's related rates and motion. It says, suppose that two motorboats leave from the same point at the same time. One of them travels north at 15 miles per hour. 15 miles per hour is a rate. The other one travels east at 20 miles per hour. That is a second rate. How fast will the distance between them be changing after 2 hours? Well, that's going to be helpful because we know their rate and we know their time. And rate times time equals distance. So that's going to be useful. Let's draw this. If the two boats leave from the same point, one of them goes due north, the other one goes east, and the one traveling north is traveling at 15 miles per hour. Well, that is our dy dt. And we have another one traveling east at 20 miles per hour. That is our dx dt. But after 2 hours, we know that this boat is 30 miles north at 15 miles an hour, and the other boat is 40 miles east. And the question says, how fast is the distance between them changing? So now we have a hypotenuse that is changing. So we're going to say x squared plus y squared equals capital D squared for distance. And if we take these derivatives with respect to t, we get 2x dx dt plus 2y dy dt equals 2 times capital D dd dt. And we can start to plug into these. We see that, well, x is 40, y is 30, dx dt was 20 miles per hour, and dy dt is 15 miles per hour. And we can use the Pythagorean theorem to find the distance at this time. So this is a 3, 4, 5 triangle but you can use Pythagorean Theorem to verify that the hypotenuse is 5 when the legs are 3 and 4. So a 30-40 right triangle will give us a distance of 50. And now we have everything filled out and just one unknown, and we can evaluate this. So by plugging in and evaluating, you should be able to find that dt is 25. The boats are getting 25 miles further apart with each hour that passes at that moment in time. So it's not. So here's another related rates with motion. Now we're talking about a point moving around a graph, and we should recognize this graph, x squared plus y squared equals 25, is a circle with radius 5. And it says, suppose that the point is moving along this graph. When the point is at negative 3, 4, its x-coordinate is increasing at a rate of 0.4 units per second. So that means it's moving to the right because it's increasing is positive. This is where x is positive. This is where x is negative. So if it's increasing, it's moving to the right. And we can say that dx dt is equal to 0.4. And just to make sense of this, if we're moving in this direction, we see that the y variables are going up. So we would expect dy dt to be increasing as well. So we expect a positive result for dy dt. That's just a little bit of graphical analysis. We're anticipating what our answer should be. So now we can take the derivative of the equation, d dt of x squared plus d dt of y squared equals d dt of 25. And we have 2x dx dt plus 2y dy dt equals 0. We know that the x-coordinate is negative 3 and that dx dt is 0.4. We know that the y-coordinate is 4, and it is the dy dt that we want to solve for. So if we multiply all of this together, we get negative 2.4 plus 8 dy dt equals 0. We're going to add 2.4 to the other side. We can say that dy dt is 2.4 divided by 8, which gives us 0.3. We can say that dy dt is equal to 0.3 units per second. So here's an application for related rates and business. It says, suppose that a company manufacturing flash drives and has the following cost, revenue, and profit equations. And we're going to discuss production output in 1 week. So 1 week worth of output, we get X flash drives. So now it states if production is increasing at a rate of 500 flash drives per week, when production is 2,000 flash drives, find the rate of increase in each of the following. So we have 500 flash drives per week as a rate that is increasing when production is 2,000. Well, X is our production numbers, so we're saying when X is 2,000, and if we're talking about the rate of change in production, that means we're talking about dx dt is 500. So now for part A, we want to take d dt of C equal to d dt of 5,000 plus d dt of 2x. That gives us dc dt is equal to 2 dx dt, and that's because the derivative of a constant is 0. The derivative of 2x is 2, but since the variables don't match, our implicit derivatives tell us to put this dx dt to follow, and we can put 500 in for dx dt. So this gives us 1,000. We're talking about cost, so $1,000, and we're talking about per week. So there is an increase of cost of $1,000 per week when production levels are at 2,000 flash drives but is increasing at a rate of 500 flash drives per week. So let's do this for part B. We want to find the derivative of r, d dt of r is equal to d dt of 10x minus d dt of 0.001x squared. This gives us dr dt equals 10 dx dt minus 0.002x dx dt. So we can say that dr dt is equal to 10 times 500 minus 0.002 times 2000 times 500, and that gives us 3,000. So revenue is increasing at $3,000 per week when production is at 2,000 flash drives per week, but increasing at a rate of 500. And then finally, part C is asking for the rate of change in profit, which is just going to say that dp dt is equal to dr dt minus dc dt, and we found each of those values. So the profit is going to be 3,000 minus 1,000, so profit is increasing by $2,000 per week when production levels are at 2,000 flash drives and increasing at a rate of 500 flash drives per week. So here are a few other examples we'll work through. This one is ripples in a pond. If a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Concentric circles are circles with the same center, and the radius emanates from that same point. As shown in the image, then the radius r of the outer ripple is increasing at a constant rate of 1 foot per second. We're talking about the radius r increasing, so it's dr dt equals 1 foot per second. When the radius is 4 feet, when r equals 4, at what rate is the total area of the water being changed? So area equals pi r squared. dA dt is equal to d dt times pi r squared. Remember that pi is a constant, so I can move it out in front of the derivative and just focus on the r. This tells me that dA dt is equal to pi times 2r times dr dt. And now we want to plug in when r is 4, dr dt is 1. So we can say that the total area of the circle in the water is changing at a rate of 4 pi feet squared per second. Feet squared because we're talking about area, and this would be the answer to our ripples in a pond problem. Next, we have an inflating balloon. It says air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per second. So this is a rate. That means we're talking about dV dt. The change of volume as time goes by is 4.5 cubic feet per second. So find the rate of change of the radius when the radius is 2 feet. So we're going to find dr dt when r equals 2. So volume of a sphere is 4/3 pi r cubed. And if we take the derivative, we see that 4/3 pi is a constant. We can move out front. So we have dV dt equals 4 pi over 3 times the derivative of r cubed. dV dt is equal to 4 pi over 3 times 3r squared dr dt. So we see we have a number we can plug in for dV dt. And we have a number we can plug in for r. So this gives us 4.5 equals 4 pi over 3 times 3 times 2 squared. And we're going to solve for dr dt. So we want to move all of this to the left-hand side through division. And we see that dr dt is equal to 0.09 feet per second. Okay, so this is the end of the lecture. Watch the video, take notes, try the homework problems, and come to class with questions.